Hi guys, this section we'll be learning about another type of transformation, which is called a rotation, which a rotation is also a rigid motion because when something moves, it will not change shape or size. So let's talk about rotations. Now in class, we are going to do all the rotations examples in class, so you really shouldn't need to watch this video unless you're either absent or if maybe you want to get ahead. But anyways, so yeah, here we go. So in class, we brainstormed some ways that we see rotations in the everyday world. Okay, so in real life, which the class came up with some really cool things. You missed out. But anyway, so some things that I've come up with. One example of a rotation are hands on a clock move around, and Ferris wheels will move around. Also, like a tire on a car will rotate, and a pinwheel will rotate. And also when people dance, they can rotate. So we got this ballerina dancer going around and around, and we have this like break dancer right here spinning on his head. It's pretty cool. Another place where you see rotations are in sports, which this video is about Simone Biles. She is a really good gymnast. And gymnasts do a lot of rotations. They also do a lot of translations and reflections. But I will show that to you in class. If you want to see it, just let me know and I can show you. But this is when Simone Biles actually created her own move, her second move actually, and she performed it at the national championship where she won, obviously because she's so good. But I'm not going to make you watch that now, so I'm just going to keep going, which yeah, it won't let me watch it. So, but anyway, so we talked about reflections, which are flips. Okay, they create a mirror image. We've also talked about translations, which is a slide and it moves to a new location. So today we're talking about a rotation, and all three of these bad boys are rigid. When they move, they do not change shape or size, which is pretty cool. So a rotation is when a figure, or it's when it revolves the figure around a given point, which usually it's going to be the origin. So like in this picture, we have the original shape rotating clockwise around the origin. Okay, so that's kind of what it's doing in the picture, which I know it's clockwise because it's going the same direction as the clock, which is pretty cool. Okay, so in clockwise, something can rotate in two kinds of ways. One of the ways is by clockwise. So clockwise is when it follows the direction of the hands. So like this, follows the direction of the hands on a clock. Sorry. And counterclockwise, that's when you go the opposite direction of the clock, like so. So you can rotate something either clockwise or counterclockwise, so be careful. Now when we rotate something, it's going to have an angle of rotation that it will rotate. It will rotate a certain amount of degrees. Okay, so if it hasn't moved, it's rotated 0 degrees. If we rotate it once, then it'll be 90 degrees usually. So like if you look here, if you ever connect a segment from a point on a figure to the origin, and from the origin to a point to the image, it will create the angle that you're rotating. So like here I connected points A through the origin, and if you see, it rotated 90 degrees, and guess what? It made a 90-degree angle. Pretty cool, right? A figure can also rotate 180 degrees, which is when it has rotated twice. Okay, and again, if I connect the pre-image point to the image point through the origin, it makes a 180 degree angle, which is a line. Alright, and then lastly, when it rotates 1, 2, 3 times, that is when it has rotated 270 degrees. And again, when I connect point A and A prime through the origin, it will create that 270 degree angle, which is pretty cool. And again, these are up here, I rotated, and down here through counterclockwise, so be careful. So in class, we did this activity to figure out how we rotate things different amounts in different directions. And we also were trying to find some shortcuts. So in class, I made you guys plot the points and trace it on patty paper and rotate the patty paper. But some people are like, Miss Long, well, I don't got time for that. Is there a shortcut so I don't have to use my patty paper to rotate things? Well, there is. So in class, we graphed the pre-image on our paper, and then we rotated our patty paper 9 degrees clockwise, so 90 degrees that way, if you guys see. And we used our patty paper to get the new shape or our image. And then we were able to come up with our points. Okay, so again, these all have shortcuts. So if we can use a shortcut, might as well, right? So if you guys see here, the points, they look similar. They kind of look like maybe they're in different places, and some of the signs look different. So the rule that we use, so on your paper, you'll be doing this on that paper. There's a little star where I'm going to have you write the rule. The rule for a 90 degrees clockwise rotation is y negative x. Okay, so what that means, if you see x and y have swapped places, like the 3 and the 2 swapped places, over here the 1 and the 5 swapped, and the 5 and the 4 swapped. But if you guys notice, all the original x's changed signs. Whoa, holy hot dog. So when x moved into the y spot, they all became negative. Okay, so our rule is y negative x, and what that means, the x value changes signs from the pre-image, and then your x and y swap places. So you change the original x signs, and then they switch places. So this spot is for if you want to practice the rule. Okay, so what I did, I went ahead and put my negative signs in the new y spot, which is going to be my original x. And then I placed my x's in that spot, and then my y's in the first slot. So there's two ways you can think about this. You can either change the sign on x and then flip, or you can flip the points and just know that your new y's or your original x's will change signs. So you have to be careful. Don't overthink it. And that would give you your new set of points. So you can use this nifty rule instead of turning your patty paper, which is cool. And then we did the same thing in example 2, which I'm not going through example 2 with you. Example 2 is actually going to look identical to example 1. You have the same pre-image points, but on example 2, you had to rotate it 270 degrees counterclockwise. So 1, 2, 3 times. But in class, my super smart students noticed that when they rotated it counterclockwise 270, the triangle landed on the same image. So it looked like this when they rotated 270. So guess what, you guys? Rotating 90 degrees clockwise is the same as rotating 270 degrees counterclockwise. Holy hot dog, right? So both of those will map onto the same image. So you can either rotate 90 degrees clockwise or 270 counterclockwise, and you'll end up with the same image, which is pretty neat. Let's keep going. So example 3 and 4, same thing. We plotted our pre-image points on our nifty graph. Okay, and then this time we are rotating 180 degrees clockwise about the origin. So we had to turn our patty paper 2 times. So we plotted our points, then we turned our patty paper 2 times, and it landed right there. And then we got our image points. So again, you guys, don't forget, if you ever connect a point to its image, so I connected A and A prime, since I'm rotating 180 degrees, it made a straight line. Pretty cool. So we rotated 180 clockwise, and it landed here. But again, there's a shortcut. So looking at the points, you know, my x's and y's, they kind of look the same, but something's different about the signs. Let's see. Negative 2 transformed into positive 2. 3 transformed into negative 3. 1 transformed into negative 1. 5 transformed into negative 5, and etc. Do you see the pattern? Do you spot it? Oh man, you guys are so talented. You're so gifted. Okay, so you were correct. So what happens? X and Y don't swap this time, but all the signs will change. So our rule is going to be negative X, negative Y. Now remember, that negative sign doesn't mean it's always negative. It means the sign will change. Like negative 2 will become 2. And positive 3 will become negative 3. Okay, so you just simply change the signs of all your points. Okay, so if you want to practice the rule real quickly, all I did was I threw some negatives up in my points, and I filled in my x's to where they already were, and my y's where y's normally go. So x's here, and then y's here. Now, I threw the negatives to kind of show you what's going on behind the scene. Like here, remember it says negative x, so technically there is a negative sign in front of my x point, but since there's a double negative, that's why that turned positive. So if this is too complicated, if you're like, Miss Long, there's too much going on. Just know that you changed the sign. So you don't have to go through all that, but if you just change the signs, then bam, you get your points. Cool, right? Now example 4 was, again, the same thing. We had the same pre-image points. We plotted it. But on that one, we had to rotate 180 degrees counterclockwise. So we went the other way with our patty paper. Okay, and this time, guess what, you guys? It landed in the same spot. So we ended up with the same image points in example 4. So guess what? A 180 degrees clockwise rotation is the same as a 180 degree counterclockwise rotation. Oh man, that's just so cool. So cool, right? So example 4 followed the same idea, and we found out that those two are equivalent. Cool beans, right? Let's keep going. Okay, now example 5, same idea. We plotted our points on our patty paper, or on our paper, and then drew it on our patty paper. This time we are rotating the points 270 degrees clockwise. So we followed the direction of the clock, and we went 1, 2, 3, because 270 will be 3 90-degree rotations. So it landed right here, so we got our image points. And again, if you connect a point to its image point through the origin, you should get the correct angle of rotation, which is pretty cool. Okay, but again, there's a shortcut, so we don't have to keep using patty paper. Unless you like the patty paper, then you are more than happy to keep using it. So if we see our points, again, kind of look the same. Some things look like they've switched around. Some of the signs are different. So the rule for when we do a 270 degrees clockwise turn, x and y switch places, but the original y's become negative. Okay, or you can think of it, you can make your y's negative, then flip your points. Or another way to look at it is that you flip your points and the new x's change signs. So whatever makes sense to you, you do. So that's our rule. So again, the original y changes signs from the pre-image, and then x and y swap places. So that's how I look at it. So like in my picture, or if I'm going to practice the rule, I went ahead and filled in my negatives in front of the new y spot, or my x spot kind of. And then I just put my y's over here and my x's over here. So bam. And that gave me my new points. So, and again, don't forget that negative sign. Don't let the demon cats get you. It means opposite, not negatives necessarily. So be careful. And then example 6, you're probably seeing a pattern. Example 6, we have the same pre-image points, but this time you had to rotate 90 degrees counterclockwise. So we took our triangle and went the other way one time, 9 degrees. And guess what, you guys? It landed on the same image. So guess what? A 90 degrees counterclockwise turn is the same as a 270 degree clockwise turn. Whoa, right? So if you rotate either way that many degrees, these two are equivalent. So, and that should happen every single time. There's always an equivalent counterclockwise angle to a clockwise angle, because if you rotate one way, you're bound to run into the other way as it's rotating. So that should always happen. Now, the next thing we did in class, we did another activity. So this should be on another sheet of paper that I have to give you. It's in the packet. And we are talking about rotational symmetry, which in class we've already talked about reflective symmetry. Rotational symmetry, what that means is that you rotate a figure and it looks like the original before you get all the way around. Or it basically tells you, as you're rotating, does the figure ever look like the original? So there are some definitions we are defining at the top of your paper. The first one is rotational symmetry, which is what I was kind of just describing. So make sure you copy this down onto your paper. So rotational symmetry is a figure A figure can be mapped onto itself by a rotation about a point through any angle between 0 and 360 degrees, which 360 degrees is a full rotation. So basically, a figure can be mapped onto itself or look like the original at any point when it goes from 0 to a full rotation. So it might look like itself more than once. It might only rotate 360 and get back to the original picture before it looks like itself. So sometimes we have rotational symmetry, sometimes we don't. Now the order of rotational symmetry, what that is the number of positions in which a figure can be carried onto itself. This is called the order of rotation. So basically, this is how many times can you rotate a shape and it look like the original before you get all the way around. Because sometimes you can rotate something and it looks like the original picture before you do a full rotation. So the order will depend on how many times that happens before you get to a full rotation. Okay, so this is order of rotational symmetry or rotation order. Either of those mean the same thing. And lastly, the angle of rotational symmetry. That's actually how many degrees you rotate to get the figure to look like the original, or how many degrees around the circle you have to rotate a figure so that it is carried onto itself. So this is like how many degrees do you rotate it and it'll look like the original picture. Okay, which sometimes it's a full rotation, which is 360. If it was like a half rotation, it'd be like a 180-degree rotation because half of 360 is 180. Look at that. So then in class we did an activity to kind of explore different types of rotational symmetry. Before we did that though, we went over some of the figures on that same sheet of paper that you're writing the definitions on. So it says, how many times can you rotate these figures to get the same image before returning to the original image? So like, let's think about this. How many times can I spin this picture to make it look like the original? Now, the original does not have this pink spot in it. I've done that so when I show you, you can kind of see how many times it rotated before it got back around and looked like this. So, like on this one, it was 2 times. Okay, if you rotate it once and this end is over, and this end is over here, which that's why I shaded it in so you could see where it was in the rotation. You can rotate it like this, and if you see, the picture looks the same. I know this one has a pink one on top and this one is on the bottom, but the shape is the same. And then if you keep rotating this back up, you'll get it back to the original. So this one rotates 1, then 2 times before it gets back around. Now, how many times can you rotate this S around so that it looks like the original? And again, this little pink dot right here just will show you where the S has been rotating. So ignore that when you're coming up with it. So let's think about it. This one is also 2 times. You guys are so smart. You like always know the answers to my questions. Man. Alright, but anyway, so like one time when this end ends up on the bottom when it rotates, guess what? The S looks like an S still. And then when this end goes back up to the top, it will look like the original. So this one has a rotational order of 2. Or since you can do this 2 times, the order is 2. Now, how many times can you rotate this picture so that it looks like the original? And again, we're still ignoring the pink. Holy hot dog. It is 3 times. Okay, this end, when it gets here, it will look the same. When this end then moves to there, it looks the same. And then when this end goes back up to the top, it will look like the original. So the order of symmetry for this one is 3 because you can rotate it 3 times before it gets back to the original spot. Same with this one. This one will also rotate 3 times. It'll go from here to there and then back up to the top, and it will look the same all 3 times. So this one also has a rotational order of 3. Nifty, right? Cool. Alright, so then you kind of explored this a little bit more, and then, so you did that on the next page. On the final page, we are looking into rotational order and angles of rotations for regular polygons. which actually, sorry, before we get there, I went over more of the paper with you. So let's back it up. So we did this, then we went over this. Okay, so like this one only has order of 1 because this thing has to rotate one whole time to get back to the original picture. This one we said 2, 3, and 4. So if something has a rotational order of 1, it actually means the figure has no rotational symmetry, because if you had to turn the thing all the way around until you got back to the start place, then it never really looks like itself. So order 1 technically means it does not have rotational symmetry. So just be careful. Let's see here. Yes. Now, the final thing we were talking about is the degree of rotation. Like, since this one had order 2, if you're rotating something 2 times, that means the order rotation, or the angle of rotation, 2 divided into 360 is 180. So you rotate 180 degrees, and it will look like itself. This one, since it rotates 4 times to look like itself, it's actually only rotating 90 degrees each time to make the shape look like itself, which 360 divided by 90 is 4. So this one had an order of 3, so if you do 360 divided by 120, that will tell you how many degrees you rotate to make this thing look the same. And this one has an order of 5, so 360 divided by 5 is 72. Cool, right? So then you did the activity, and then we wanted to explore what happens when you have a regular polygon, which, remember, that's when a shape has the same lengths for all the sides and the same angle measure for all the angles. So it's equilateral and equal angular. So you guys found out from the activity that regular polygons always have the same order of rotational symmetry as the number of sides. So like an equilateral triangle, since it has 3 sides, has an order of 3, a rotational symmetry order of 3. Since a square has 4 sides, guess what? The order of it is 4. Pentagons will have 5, regular hexagons will have 6, regular heptagons, that's one that has 7 sides, will have 7, and regular octagons will have 8 for its order of rotational symmetry. So pretty cool. Then you're also trying to find a pattern between how can you find the angle of rotation real quickly for a regular figure, which we found out for a regular polygon. What you do is you do 360 divided by the number of sides. If you have a non-regular polygon, you can't necessarily divide by the number of sides, but you divide by the rotational order. So that's kind of like what I was going over here. Like this had a rotational order of 2, if we think back to this slide. It had a rotational order of 2, so its angle of rotation is 180 because 2 into 360, which is 1 full rotation, is 180. So to get back to that slide, if it's not a regular polygon, it's 360 over the rotational order. If it is a regular polygon, you don't have to necessarily know the rotational order. As long as you know how many sides it is, then you're good. But remember, with a regular polygon, the rotational order is equal to the sides. So these two are kind of the same when you have a regular figure. It's either the number of sides, which is equal to the rotational order. So you could technically divide 360 by the rotational order also for a regular polygon. Or you can do it by its number of sides. So either way. All right, guys. Well, that's it with our rotational order. So thank you for watching.